made the first luminescing tubes. So, okay, just feel free to check this out. And if you have any questions you can think of, just let me know. Okay, so but let's get started with the lecture. So, of course, we again repeat. Oh, so one is asking where I posted it, so maybe not all see it. So let's repost it again. So here you go. Okay, so let's see what we did last time. So we started by solving some tasks. So a task related to the cross parity check code, which is also like a part of your homework, which you can solve. And this cross parity check code is quite easy to understand. So we can imagine like arranging our information bits like in a square shape and calculating parity bits for each row and each column. And of course, then at the receiver, if we recalculate the parity bits based on what we receive, we can basically identify mismatches between the received and the calculated parity bits. So we can say something's wrong in this row and something's wrong in this column. So it can only be this bit to cause this kind of error, and we just invert it, and this way we correct it. So we can correct single errors by using this kind of cross parity check code. So depending on the pattern, we can also correct double errors, but this we could think about when we would go a bit deeper in this cross parity check code. Imagine here another bit wrong. Oh no, this would already be difficult. Then this parity would match. We would get a wrong parity here, a wrong parity here, but we could not tell the row. So, but there might be some error patterns with two errors that can be corrected. Okay, but let's do not go deeper there. So we continued with another task where we treated again this generator matrix and the parity check matrix H for two very simple codes, the repetition code. Of course, we can also describe this encoding routine by a matrix vector multiplication. So if we multiply just with a, in this case, the matrix turns into just a row vector containing ones. And if we multiply our information bit with this generator matrix here, we get the code word. So very simple generator matrix for our repetition code. And we can also provide the parity check matrix here, H being basically the parity matrix transpose. There's two columns here, so I can also illustrate this again. So the parity matrix transpose is how this parity check matrix starts, followed by an identity matrix. And this will be the rows being orthogonal to all our valid code words. So just note here again, the rows of H are orthogonal to the rows of G. So if you build the scalar product, if you multiply each of them, the result will be 0. So this is this orthogonality which we try to illustrate in this one drawing with the spaces where we saw the spaces. Okay, then we did the same for the single parity check code, so of an arbitrary size. So we have n information bits followed by one parity bit. So we have code words of length n containing n-1 information bits. And also this can be described by a generator matrix. So where we basically get the parity bit. If we want this to be the sum of all the information bits, we can get this here by a column in the generator matrix containing only ones. This means 1 times 1 plus 0 times 1 plus 1 times 1. So everywhere where I have a 1 in my information sequence, I will get a 1 in this sum here at the end. And of course, we also want the information bits to be a part of the code word, and we simply get this by using this identity matrix here at the beginning of this generator matrix G. So two very simple examples, to get some more exercise, some more practice with this generator matrix, how this works and what it means. Okay. Then we thought about a method how to decode these block codes efficiently. So far, we only learned that we could decode the codes based on the minimum Euclidean distance, for example, if we have a real value channel output, so a soft decision decoding, we would use the Euclidean distance. For a hard decision decoding, we would simply use the Hamming distance. So always the question, finding the valid code word being most similar to my received sequence. But if we have large sets of code words, this means we need to calculate really many Hamming distances or many Euclidean distances, of course, which we want to avoid. So we thought about a more simple method, how we can actually implement the decoding. And this is the so-called syndrome decoding using standard arrays, or sometimes they are also called cosets, using cosets. And let me explain again what the story was behind this. So we already know we can calculate the syndrome by multiplying our received sequence with H transpose. So we know H transpose, the rows of H are orthogonal to my valid code words. So the columns of H transpose will be orthogonal to the valid code words. So if Y will be a valid code word, the syndrome will be 0, because then Y will be orthogonal to the rows, to the columns of H transpose. So if Y, valid code word, the syndrome is 0. If some errors occur during transmission, the syndrome will be different from 0. And then just the question is, what went wrong if we observe a certain syndrome? Here, our model, basically, how we model this transmission. We transmit a valid code word. We receive any sequence because errors can happen, as we describe by this error pattern E. So for example, if I transmit a 111 and I want to model an error in the last position, I could simply do this by adding this error pattern with the 1 at the last position. So you see, where the error pattern has 1s, the bit value will just flip. If I have a 1 here, the outcome will be 0. So this introduces an error. Or if I had a 0 here in the transmitted word, adding a 1 will make it to 1. So a 1 in the error pattern will always flip the value of my bit. So this is the way how we can introduce or how we can model errors here in our sequence by adding this error pattern. Okay, so this was the basics for the further thoughts. So then we basically described the syndrome by multiplying Y times H transpose, where Y is a valid code word plus our error pattern. So just inserting this here for Y, and then we can multiply this out and we get A times H transpose, which we know A is a valid code word. If we multiply it with H transpose, A will be orthogonal to the columns of H transpose, so the result will be a 0 vector here, so we can forget about this one. And the syndrome basically just depends on the error pattern. So for example, if we go back to this example here, if I transmit 111, the last bit is wrong, so I receive 110, I will get the same error pattern as I will get the same syndrome if I transmit 000 and the last bit is wrong and I receive 001. So for Y001, I will get the same syndrome as for 110, because the syndrome just depends on basically the positions of the errors, on the error pattern. So this is important later on to understand this coset table correctly. So just the positions of the errors are important for the syndrome. Syndrome will not depend on the actually transmitted code word. Okay, so then we came to an example. So if we think about the 7,4 Hamming code again, we have 4 information bits, which means we get 16 valid code words. But as our code words are of length 7, we can have 128 possible received sequences. So from this one, 16 will be correct code words, 112 will be any sequence which is not a valid code word. But we only have 3 parity bits, 4 information bits, code word length 7 means we have 3 parity bits, check bits. With 3 check bits, we can get 8 different syndromes, 2 to the power of 3. So this means not all error patterns will have a different syndrome. So we will have several error patterns which will result in the same syndrome. And this is basically what we describe by this coset table. So we basically group the error patterns which result in the same syndrome. So we already know there must be more than one error pattern having the same syndrome. So let's group them. So all error patterns with the syndrome S mu. And then we basically came up with a first approach how to get this coset, these groups of error patterns, and we could simply get them by calculating the syndrome for all the error patterns. So we started here with 1. For example, if we have an error pattern 1 at the last position, multiplying it with H transpose, we get the syndrome 001. This one here. So this means the error pattern 00001 is a member of the coset. So a member of the set of error patterns which will result in the syndrome 001. And I just wrote down here the other ones which basically end up in this coset. You could also verify this by multiplying any of these error patterns with H transpose. The result will be always 001. So those 4 are the error patterns with the syndrome 001. And then we just had to think about if we observe now a syndrome 001, which error pattern most likely occurred. And there it is more likely that only few errors occurred, as if, for example, 4 errors occurred. So if we would model again a binary symmetric channel or an additive white Gaussian noise channel, the probability that this one happens here will be higher as if 4 bits on. So we basically select the so-called coset leader by selecting the error pattern with the lowest number of ones from such a coset. So here our coset leader is this one here with just the 1 at the end. And we basically would do this for all other syndromes. But we will talk about this today again. But first, it's important to understand what this coset means. The coset, again, it's the error patterns which will result in the same syndrome. And today we want to get to know a smart way how to get this whole syndrome tables more efficiently as by calculating the syndrome for all error patterns and then just sorting them. So this would be like the brute force approach, calculating all this or for all 128 error patterns, calculating the syndrome and then sorting them. Okay, we will get to know a better way. Okay, and then if we basically know this coset table, we can use it to correct errors. So for example, if we receive a certain sequence, we basically just calculate the syndrome by multiplying here with H transpose again. Getting the syndrome. And with the syndrome, we look in our syndrome table and we find the most likely error pattern. So if we receive a 11110, most likely the second bit was wrong. So if we add our error pattern, this will again just flip our second bit and in this way correct the mistake, which means most likely this code word here, A hat, was transmitted. And if you look back to your set of code words, you will see, of course, this is a member of gamma, a member of the set of valid code words. So this is basically how the correction works. We receive any sequence, we calculate the syndrome, we look up what went wrong, most likely if we observe this syndrome, and by adding the error pattern, we correct the error. So this is basically how this syndrome decoding works. Yes, are there questions related to this? But we will talk again about this today. But this is important that you understand it, because it could be that we have a similar task in the exam. So maybe just to give you this as small hint, try to understand this and try to be able to solve that kind of questions. Also today we want to solve a question related to this coset factorization, to the syndrome decoding. Okay, but before we do this, we want to get to know a smart way how to determine this coset table. And but before we start, let me give you a hint for the students in Kazan. I talked to the guys from Kazan, and you will have the exam on January 24th from 10 to 12 o'clock. But I don't know the room now, but probably the colleagues in Kazan will tell you. I will also talk again to them in January. And who knows, maybe I still get the chance to travel there. But actually, I'm still waiting for the invitation there. Okay, but let's start again with the theory. Efficient way to get the coset table. So we start again with this M mu being all error patterns for which the error pattern multiplied with H transpose turns out to be the syndrome S mu. Maybe let's write it again. Group of all error patterns which yield the syndrome S mu. Now let's take two members from this set. Let's take two members from M mu say E and E prime. Then, of course, E times H transpose will be S mu. So actually, we could also pick a specific S mu here now, but I just want to indicate that it will turn out to be the same result. E prime times H transpose will be also S mu. So this means E times H transpose will be the same as E prime times H transpose. Or bringing it to one side, so this means E times H transpose minus E prime times H transpose will be 0. Or let's factor out the H transpose. Again, we need to be careful if we are dealing with matrices and vectors, but here it's okay to do it. E minus E prime times H transpose is 0. Well, and we know anything that we multiply with H transpose and the result is 0 must be a valid code word. Because it's again orthogonal to the columns of H transpose. This means E minus E prime must be a valid code word. Let's call it A or AI, one specific code word. So if E minus E prime is AI, then I could also say E is equal to E prime. It's not writing here. So equal to E prime plus A. So this means we get a member of our coset mu if we already know a member and we add a valid code word. We can get a member of mu if we know one member and if we add a valid code word. And of course, these are just, it's an arbitrary code word here. We didn't make any constraint on which AI to select here. So this means if we select all possible AIs, we will get at the end all members of this coset. So more general. So if we consider E plus like the whole set of code words gamma, so this will be then E plus all possible A's for all A element gamma. And this will be my coset M mu. So this means if we add all possible code words, if we add all possible code words, comma, we get the complete coset. Maybe let's draw a box around this. And I will show you again in the example how this makes life easier now for us. So there, let me look again on this example that we had. So, unless there are questions so far, then we answer the questions first. Otherwise, we go back to our example for this 5,2 code, I think it was. So back to the example. So here's the question in the chat. Oh, of course, everybody can read it now. That's the advantage of completely online. So the question is if the valid code words are given beforehand. Yes, so usually we know the valid code words because typically we know the code by defining its generator matrix. And if we know the generator matrix, we can simply calculate all of the possible code words by multiplying the info words with the generator matrix. So getting all possible code words is an easy task. Okay, so let's come back. We had the code words in our example. So 4 valid code words, the all 0 code word. Then we had the 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, and the fourth one being 1, 1, 1, 0, 1. So these were the members from our set of code words for this example, and we wanted to come up with this coset table here, M mu coset. So see. So we will get 4 members in my set of code words, in my coset. So first, here we have the syndrome S mu. Up again, so this coset table, we already made this. Now I show you how to get the rest easily. So we start with the syndrome 0, 0, 0. And keep in mind, the coset contains error patterns. It does not contain code words. But nevertheless, of course, the error patterns resulting in the 0 syndrome will look the same as our valid code words. Because you could imagine if you have an error pattern looking like this, meaning no error occurs, no matter which of the code words you transmit, it will be a valid code word, no error appears, valid code word at the receiver, syndrome will be 0. So if this error pattern occurs, syndrome 0. So, and then of course you could also imagine if you are facing this error pattern. Just imagine you transmit the valid code word being 0, 0, 0, and this error pattern 1, 0, 1, 1, 0 occurs. Then, of course, your received sequence will look exactly the same as the second code word. So again, the syndrome will turn out to be 0 if this error pattern occurs. So basically, you notice that the error patterns looking the same as our valid code words will turn out the syndrome 0. So here we will select this coset leader to be the pattern with the lowest number of ones, which in the first case is the 0, 0, 0. Maybe we write this as side note. Notice mu contains error patterns for the syndrome being the 0 syndrome, the error patterns are identical with, let's just write gamma.
Which means no error, right, sir?
Yes, exactly. This means no error. Or well, it can also mean, for example, if you look at the second guy here, it can also mean 3 errors. So for example, if you transmit 0, 0, 0, 0, the first, the third, and the fourth bit are wrong, you will receive a 1, 0, 1, 1, 0. Syndrome will turn out to be 0. Your decoder will say, correct transmission, no error appeared. But actually 3 errors appeared. But our code is just not powerful enough to detect this or to correct this. Okay. So then we thought about how to complete now this kind of table. So let's do this one. So we had the 0. Let's see what happens, what syndrome we get if we receive a 0, 0, 0, 1 multiplied with H transpose. I think we did this already. So let's look this up from before. Yes, it turns out the syndrome 0, 0, 1. So for the syndrome 0, 0, 1, I know the 0, 0, 0, 0, 1 is a member of this coset. And now with what we just derived, if we say, okay, this first coset here is identical with the valid code words, and I know if I know one member of the coset, I can get the other members by adding this error pattern with the valid code words. So I can simply get the next one here. So let's see how we can illustrate this nicely. So actually, this one's up here, are identical to gamma. And we now share screen. If we add a member of gamma with our already found error pattern from this coset, we will get another member of the coset. We add these two guys, we get the 1, 0, 1, 1, 1. And you could verify this. If you multiply this guy with H transpose, you will also get the syndrome 0, 0, 1. You add this guy, you get the 0, 1, 0, 1, 0. Also, this will be a member from this coset. And of course, also the last one. You add this guys. You will get just also the last bit flipped. 1, 1, 1, 0, 0 will be a member of this coset. So basically from one member of M mu, we can simply get the whole coset. This is actually what we did here in green. And then again, selecting the coset leader, so the most likely error pattern, so meaning the error pattern with the lowest number of ones, which will be here the first one. And this way we could complete the table. So let me just bring another one. If we use this one to calculate the syndrome, of course, for one, we need to calculate it. We will get the 0, 1, 0 syndrome. And you see, it's similar easy to get this now. Again, by adding the valid code words. Just want to use too many colors here. So if I add it with this guy, see the fourth bit being flipped. So then this one will be 1 0 1 0 0 0 1 0 0 1 1 1 1 1 1. And again, selecting the coset leader, and so on. So this saves us some work. So meaning we don't have to calculate the syndrome for any possible combination of errors. So for all the error patterns, we simply need one member from one of the cosets, and we add the valid code words to get the remaining members of this coset. Maybe it's good to show you this also on the lecture slide. Let's see something more here. Let's pull up this one here. So here you see the complete coset table with the coset leaders here always chosen. And the last two rows are interesting because you see in the last two rows we have at least the difficulty selecting this coset leader because we have two patterns containing two ones. So here it's unsafe whether we select this first one or the last one as coset leader. So this just means the case where two bits are wrong. First one wrong and second one wrong, or third wrong and fifth one wrong. We cannot distinguish them. So with 50% probability, just flipping the first two bits will correct this double error, but also in 50% of the cases, this syndrome occurred because of the third and fifth bit being wrong. So then correcting the first and the second one will fail. So, but for all single error patterns, look at this one. The first one, second, fourth, fifth. So all single errors can be corrected. For the double errors, we have some probability here that things will go wrong. Also in the last row, we have here two ones here and also two ones here. So also there with 50% probability, this double error could be corrected. With 50% probability, things will go even more wrong. Okay, let's get rid of this. So this just as method how to get these cosets efficiently. Okay, so then here we have another question. How do we know the number of error patterns are equally partitioned between the cosets? Okay. So we basically can get the idea on the size of the cosets by looking at, see our example. Just so look again at this generator matrix. This tells us we have two information bits going in here, meaning we get 4 valid code words. So from this, I already know we will have 4 members in each of the cosets. And then how many cosets we will get, this depends on the number of check bits. So if our code words are of length 5, we have 2 information bits. There are 3 check bits. With 3 check bits, I can distinguish 8 different syndromes. So this means at the end, this table will be of 4 by 8. So 4 times 8 will be 32. Well, and of course, actually 32 is also what we get from this length of the code word. Of course, we can have 2 to the power of 5 different error patterns that we can group in. In this case, it will turn out to be 8 cosets, each having 4 members. Yes. Okay, some more questions related to this one. Otherwise, we would come to a task. Okay. So actually, I want to copy in here an exam task that we had a couple of years ago. This one. Okay. So because it's a lot to write, so therefore I almost completely prepared this table for you in the exam. But anyway, it's still an interesting task to solve. And there I would give you again some time to try to solve it on your own. And yes, then we will see if you are able to solve it, or you will see if you are able to solve it. And let's just give you some time. Okay, so try to solve this one and give me a hint if you are done, or also write if you have difficulties solving. So we already have some good solutions for A. It's okay. Well, we can solve A already. Already see the H matrix, so some already got H. Already see some H matrices here, so we can also solve this one. As we know, G. So let me see. So the H matrices from the chat look okay. Some already got the missing members from this first coset. So actually, okay, let's have a look at task C. So there I gave you the hint that this row can be more easily completed as you might think. So of course we already know the syndrome 0. Here, these error patterns will be identical with the valid code words. So these last 4 guys must be valid code words. And also these missing ones must be valid code words. Now just the question is how to find these missing code words. And it was actually thought this way, that you know that all the rows of G will be valid code words. And of course, also all the linear combinations, meaning also the all 0 code word must be a valid code word. And if you look at these ones down here, valid code words, and if you look at the rows of G, you see exactly the ones that are missing are the ones which are the rows of G and the all 0 code word. So this is basically the all zero code word. This is missing. And the first row of G. Second row of G. And the third row of G. Let's also use some color here. Because these rows are element of gamma. And this whole first coset, this is basically the same as gamma. So this was basically what my hint was meant for. You need to find the missing members of gamma here to complete this coset, and you can easily get these missing members, as you should know that all the rows of G are valid code words. And if you look at the ones, you see that these are the ones which are missing down. And also the all zero code word is a member from the valid set of code words. Or thinking again in terms of the coset, the all zero error pattern will always result in a valid code word at the receiver. So if no error appears, we will always get the zero syndrome at the receiver. So this is also why here the all zero sequence must be a member of this coset. Okay. So then we just need to select the coset leaders. Well, this is straightforward then, finding the ones with the lowest number of ones. Just, do we have here one with a single one? Yes, this one. One at this position. One at the second position. One at the third position. For the last one, we don't have one with a single one. So then it will be equally bad which one to choose. So I just select this first one, the 0, 0, 1. 0, 0, 1. So of course, then it could be that two errors in one code word occur and we correct them wrongly, actually insert even more errors than it was caused, for example, by this two or by this two. Okay, but again, the single errors, all of them appear, all single errors can be corrected. So the first coset leader, yes, here 0 is missing. Yes, thank you. And there was a question before related to the cosets. Why we select here the coset leaders to be the ones with the lowest number of ones. This is again the explanation that is more likely that few errors occur as if many errors occur. So we observe or we calculate a certain syndrome and we ask what went wrong most likely. And most likely fewer errors occurred as if many errors occurred. Sometimes I also explain this with an example. Just imagine you go to the doctor and you say, I feel dizzy. Then that's the syndrome, dizziness, you feel dizzy. And then there could be many reasons for this. It could be that you have like a low blood pressure. It could be you did too much sports, you have muscle pain, or it could be you drank too much alcohol the evening before. So there are many reasons that could cause the same syndrome, and just the question is what most likely appeared. And it's exactly the same with our syndrome table here. We have many error patterns that could cause the same syndrome. We just ask for the most likely one. Okay, and here another question. If the matrix G is not given, we cannot find the missing coset in row 0. Yes. Well, of course, it's more difficult then. We could also complete this table by looking which combinations of ones and zeros are missing. But of course, this is more tedious to come up with this brute force approach. But of course, it also doesn't make a lot of sense to think about a coding scheme where you don't know the generator matrix. So typically, you know either the generator matrix or the parity check matrix, and you can get one out of the other. So any of this you must know if you talk about a specific coding scheme. Okay, so there's another question. Oh no, that's it already. Okay. And then, of course, it's easy to come up with this last task, to do this decoding thing. Task D. So we receive Y. We need to multiply it with H transpose, so leave some space to the top. Receive 1, 0, 1, 1. This is Y, what we receive. Or the guy coming to the doctor, and we want to know what is wrong with him. So we multiply with H transpose to get the syndrome. H transpose, so we get it here. First row will be the first column. So this will be H transpose. 1, 0, 1. 0, 1, 0. 1, 1, 0. 0, 0, 1. We multiply this guy, we get the syndrome. So what is wrong with this received sequence? So 1 times 0 plus 1 times 1, so we have a 1 here. 0, 1, 0, 0, so we get a 1 here. 1 from here, 0, 1, 0 here. 1 plus 1, 0, plus a 1 from the last guy. So this should be our syndrome. So just verify if you get the same one, or if I made a mistake. First one, just recheck. Fourth one. Okay. Oh no, the first one should be a 0, no? So it's a 1 here, 1 plus a 1 from the fourth one, 1 plus 1 will be 0. Yes. Yes. Okay. So we have the syndrome 0, 0, 0. Zero, zero, 1. So this is the syndrome that we found. So most likely this error pattern occurred. For 5. 5 zeros and last one of 1. So also here I missed a 0. Wait. My code words are of length 6. Okay, so I was missing some zeros here. Okay. Yes, so obviously if we observe the syndrome 001, the last bit is wrong, so we can get A hat. Y plus E. Yes, so I have not more space now, otherwise I would write them upon each other and do this addition, but you can easily see that adding this last bit, being a one bit, will just flip the last one. So if we observe 110, 111, most likely the valid code word 110, 110 was transmitted. So this is what our coset decoder, our syndrome decoder tells us.
Professor?
Yes.
I have a question like, do we need to calculate E error by using H transpose multiply Y multiply by H transpose? We can directly get it from the table, right? Here we have the table, and when we look, if it contains all the Y's received, and if we look 110, 111, it comes under second row, I think.
Yes, let me
Column.
see if I understood it correctly. So you are wondering why we need this syndrome calculation and the syndrome table at all. We could also, of course, we could also do the decoding based on the minimum Hamming distance. We could basically compare this received sequence to all my valid code word and see which one is it most similar to. And there we will see it's different in one position with this valid code word. Let's decode for this one. But in order to do so, we would have to calculate 1, 2, 3, 4, 5, 6, 7, 8 Hamming distances to find the best estimate. Whereas in our syndrome decoding, we just need a lookup operation in a table, which we just need to store once. We need to calculate the syndrome and look up the error pattern. Maybe that's from the computational complexity in this example, still similar, like calculating 8 Hamming distance is also not really a big deal as compared to calculating the syndrome and performing this lookup operation. But if we have really larger sets of code words, like 10,000 different code words, then of course the syndrome decoding will be superior in terms of complexity as compared to the maximum likelihood decoding, calculating all possible Hamming distances. So it's a question of efficiency, because of course we only need to calculate this syndrome table only once. And we actually need only this column and of course the syndrome. So calculated in advance, calculated before, and stored. Then simple lookup operation. So that's basically the benefit of knowing this coset table, that the error correction simply turns into one vector matrix product to calculate the syndrome and one lookup operation, look up the error pattern that caused the syndrome. Okay, so there we have another question. If there are two values with the same number of ones, which one needs to be taken as coset? Okay, so this question basically refers again to the last row here, for example. You are asking, let's use a different car here. We don't have a better red. Ah. So basically the question is what to do here. So first of all, if we would look at the minimum Hamming distance of our code, we would see it has a minimum Hamming distance of 3, so it can correct single errors. So in case 2 errors occur, we cannot correct them. So, and this is actually true for this last coset. So there we only have 2 bits being wrong, which can cause the syndrome to be 111. And there are 3 different patterns which can cause this. And of course, the best we can do is selecting any of these 3 patterns. And in 1/3 of the cases where the syndrome 111 occurs, we would actually be able to correct the errors, because in 1/3 of the cases, actually these 2 wrong bits will have caused the syndrome to be 111. But in 2/3 of the cases, things will go wrong. We would observe the syndrome 111, we correct the 3rd and the 6th bit, and it would be wrong. So in 2/3 of the cases where 2 errors occur for this syndrome 111, we would fail. Our code is not strong enough. So let's write here, select any. I think that's enough. Select any. Okay, so are there more questions related to this? Okay, so it's just a way to efficiently decode especially larger sets of code words where we want to avoid calculating all these Hamming distances, which we would have to calculate for the maximum likelihood decoding.
Sir,
yes.
Always we select the syndrome's corresponding coset leader as our error, like finding D problem.
Let me see if I understood.
We got the syndrome 001. It can be any of the cosets, but we selected as coset leader.
We selected the coset leader as the error pattern with the lowest number of ones. So it could also be
any of those.
Yes, it could also be that we transmit, for example, the valid code word. Let's take this one, 100011, and the last 4 bits are wrong. This could happen. We would receive 101100. We calculate the syndrome. The syndrome will be 001. We would say the last bit is wrong, but actually the last 4 bits were wrong. So also here we can make decoding errors if we have not the lowest number of errors, but if we had, for example, these 4 errors. But again, think about the most easy channel model that you can imagine, our binary symmetric channel. The probability of 1 bit being wrong would be PE. If you ask times 1 minus PE in brackets to the power of 5. This would be the probability for this one. And here you would already get a probability of PE to the power of 4. So very unlikely.
Okay, so we have taken very likely to happen, that condition.
Exactly, yes.
Most likely, yeah.
That's why we select the coset leader to be the one with the lowest number of ones.
Okay, good.
Okay, are there more questions? So, okay, so here's one. So the decoder needs to store only the syndromes and their corresponding coset leaders, not the entire table. Yes, exactly. Ronald, you understood what it is about. Yes, we don't need the whole table. We just need to calculate this table once to find the coset leaders. But then what we need for the decoder is really just the coset leaders and the corresponding syndromes. This is all we need. Look up the coset leader for the syndrome that we calculate. Okay, more questions. Okay, so very good. So we can already come to our next topic, at least to the introduction of the next topic. So actually I rearranged the order a little bit. So I don't want to talk about the convolutional codes next, but about the low density parity check codes. Low density parity check codes. LDPC. Used, for example, in 5G. So I rearranged the order a bit because the convolutional codes and turbo codes are not so relevant anymore, but the LDPC codes became more important and the polar codes. And this is why I treat the LDPC codes first, because also the students in Kazan will get an exam question related to these LDPC codes. And the convolutional codes, we can treat them also after the exam in Kazan, for example. Okay, so let's look what these LDPC codes are about. Actually, I wrote some facts on the lecture slides and just the main ones proposed. Already in 1962 by Gallagher. So this was the famous guy. But the computational complexity was too high. Computational in the 60s. Let's write here huge parity check matrices. So for example, you could have like parity check matrices having like 10,000 rows and 20,000 columns. And this was for the 60s really a big deal to do this kind of computations. Or the memory was already the problem there, how to store such large matrices in order to process them somehow. Today, it's no problem anymore. This is why we see this kind of codes in 5G, but they have been already used in DVB-T, have been used. DVB-S, so satellite TV. And for what you understand so far, they are just normal block codes. Just block codes. With large and sparse parity check matrices. And we will see why this is useful. So sparse means only few ones, mostly zeros. The decoding is done typically iteratively, which makes it a bit more difficult. Typically iteratively. But we will see how this actually works. Yes, and maybe the last 4 minutes are enough to introduce already the so-called Tanner graph. Important. Representation. So-called Tanner graph. So the Tanner graph basically illustrates this parity check matrix H. Let's use, for example, let's say we treat the 7,4 Hamming code as if it was a good low density parity check code. We know the matrix H. Let's write it here on my slide. The 1, 1, 1, 0, and then followed here by an identity matrix. 0, 1, 1, 1, and 1, 1, 0. And now we simply illustrate this by so-called check nodes and bit nodes. Check nodes. And we can simply imagine this three, 4, 5, 6, 7. And this tenor graph basically describes which bit nodes or which bit values basically contribute to a certain check node. So, or we could say the first bit in our syndrome is calculated by using the first, second, third, fifth of the received bits. So we have here links from the first bit, from the second bit, from the third, and from the fifth. So this tenor graph basically describes how the bits in our syndrome are calculated. This is basically just the first one. Oh, let's also use some color so it will be more easy for you to understand. Use the light blue. So we use the second, third, fourth, and the sixth. And another color. We use the first, second, and the last one. And this is basically what we will use next time when we talk about the decoding, how we can do the decoding. You already can get an idea. Of course, if I calculate the syndrome by using this H transpose and the syndrome turns out to be 0, we have a valid code word. So at the end, we will have to think about how could we make this check nodes to be 0? Or what are the probability that the sum of these check nodes turns out to be 0? So we will talk about things like this next time, starting with a very simple example, but then we will see actually if we want to understand what is going on in 5G, we need to dig a little bit deeper there. But for the beginning, this is actually fine to get started. Bit nodes. But we will continue there next time. So just as introduction. Okay. Do you have questions related to this? Okay, so then we will meet again on Thursday and continue there a bit. And yeah, let's just see how far we get before the Christmas break. And yeah, otherwise we will continue with this one in January. Okay, so then thank you for your attention and have a nice afternoon and see you on Thursday. Goodbye.